Hello. Hello. L- Hello. Oh, good afternoon. Oh, nice, Sylvie. You win. Good afternoon, Sylvie. And hello. Oh, and that was you. Okay. Hello, Eugen, who is sick. Good to see you. Or sort of. Um, I mean, it's totally good to you get my point. So good afternoon, Sylvie. Good afternoon, Eugen. Hello, Kayla. I do love that, I have to admit. Hello, Marina. Um,
Hello.
all right. And hello, Marina's dog as well. Awesome. That just good points for. Oh, did someone just flash video? Oh, hello.
Lizzie says thank you.
Okay, excellent. Excellent. Um, uh, okay, bad dog jokes are running through my brain. All right. Hi, Ashton. Hello, Ashley. Hello, Abigail. Hi, Devin. Hello, Jake. Okay, in sepia. Not really sepia. No, straight up black and white. Film noir. Yeah. Okay, did I say hello? Is that everybody? Oh, Isabella, hello. If I didn't, Remy, hello. And I know Remy was here like 45 minutes ago. I know, or not literally, but I do understand that people were waiting even before I. Okay, all right. Hello. Oh, yes. Oh, hello, Jonathan. I'm sorry. Hello, Jonathan, who totally has watched a whole bunch of videos. I'm aware of that. I appreciate it. Okay. Okay. Another day, another dollar, another long physics 102 class. Not that many to go. Another announcement slash apology update, whatever. Some people have, and this is again just the case in all of my classes. There's many of them this semester. Some people have gotten exams back. Some people have not. The exams are just coming back far more slowly than they should, but they're coming back. Like for some reason, the older I get, the longer it takes me to do these things, and I somehow cannot pull all nighters anymore. So they're just coming back like progressively as they come. So if you have gotten one back, terrific. And if you want to speak with me about it or anything, that's terrific too. If you have not gotten one back, that reflects nothing about you personally or nothing about the quality of your work. It probably reflects the first initial of your first name more than anything else. And again, it's just a progression through all of the classes. So I apologize. I'm not going to dwell on it. Yes, I am. They're just coming as they're coming. All the dust will settle and all things will come out in the wash by the end of the semester. As we get closer to the final, if you're super panicked about that, I understand it. And you could talk to me privately and just understand that I understand. And that will be taken into account in the final and in the final grading. But all of this will come out in the wash by the time we land. I think I've said anyway. I could keep making speeches about that. I don't want to, but if at any bottom line, if there's any, and some people have already taken me up on this, by the way. Again, the bottom line is if somewhere in your gut or in your soul or in your mind you feel like there's reason for concern in this class, either because you know somewhere in you that actually you haven't been doing something, or you actually really think that you might have really done badly on the midterm and you don't know, right? Or if you're just nervous because you don't have enough information, just reach out to me by cell or by email, and we will one-on-one talk about what your situation is. And either I will just reassure you that it's fine, or if there's actually something that needs to be done, we'll find it out. But if I haven't reached out to one of you, to you, then that means I don't think there's a crisis that I have been aware of yet. Oh, and there's something in the chat. So anyway, I hate to keep making that speech, but I just want you to know again, the assumption is that we all want to do well and we're all looking to do well, and that no one's going to be shocked by at the last minute. Wait, so there's something in the chat. Sorry. Oh, that's an interesting question. Sylvie's question. I think I understand. Okay, that's an interesting thing too. Yes and no. I mean, so here's the deal with your grades. The exam, it's not like I'm holding back on you. With the terms of the midterm exam, if you haven't gotten a grade, that's because it doesn't exist yet because I'm that behind on them. So I'm certainly not withholding anything from you as far as the midterm. Now, everything else, and I've been progressively catching up on all the other things. And I think, and I might even continue to during this class, everything else, all of the game turns, all of that kind of stuff, there, I think most of those grades are in most. Anything I grade in Google Classroom. What I'm trying to say to Sylvie's question, it's a very fair question. All the grades are in Google Classroom. And if they're not, that means it's something I haven't graded yet. And you can talk to me about that personally, or it's coming. So I don't have a separate book of separate information on the one hand. I want to be very clear about this because I think I understand the nature of this question. There's no separate book. The only information is the information that's done in Google Classroom. However, I don't average the grades the way that Google Classroom does. I don't compute and put together all the final grades the way Google Classroom seems to indicate. Like the Google Classroom, to be very clear, every bit of information that's done through Google Classroom does conveniently deposit in a spreadsheet for me. I mean, that's one of the things I like about it. It puts all the data in a spreadsheet for me, but then how I tally, and that I keep separately, that you don't see till the end. I mean, it's not a secret, but that's not publicized. It's just accumulating as you go. You don't see it till the end. But all the data that's in that spreadsheet, I tally everything up with my complicated grading system, which I'm happy to repeat to you again, and which is in the syllabus and which is the same for all students, but it's not the way Google Classroom does it. So whatever Google Classroom is ever projecting as your grade, I'm not standing by that. Like that, whatever, it's just doing some straight up percentage of all your things, and they can be wildly different from what I think your grade is. So in that sense, so again, I'm sorry to dwell on this, but I know everybody, of course, you're concerned about your grades. I mean, of course, you have and I'm going to check again, I'll check again in the chat in a second to see if I'm really answering this or not. But if you're ever looking at Google Classroom to see what your grade projection is, and Google Classroom is saying something like 78% or 93%, it's true, you shouldn't trust that. You should come to me directly and say, hold on, what's really going on with my grades? And whether or not I can give you exact number off the top, I will sit with you and say, this is what's going on. You shouldn't trust the number Google Classroom is saying, but the data, I don't have any separate data that's in a book. So does that answer the question? Wait. Okay, wait, well, let me just see. Oh, so that means yes. So Sylvie is thumbing up saying she gets it. Okay, cool. Now on Marina's question, and again, I have to be careful about this too. I think these are super legitimate questions. I will say, and I don't want to run away from them. I don't want to, I don't think we all want to spend 2.5 hours on this. So again, if it gets cut off, then definitely text me or email me, and I will be. But to the extent that I can. So, oh yes, thank you. So, God, I'm gonna miss you guys. See, awesome. Just side note, do you see? Well, okay, I'll answer Marina's question and then. But no, I like the way Sylvie. See, you all have such a different way of communicating, even in Zoom. You all have such a different style, and you all do have style. Can I just remind you of that? Like your style comes through, and the purpose of the grading system, it's meant to acknowledge the fact that there's more than one way to succeed. And you guys definitely like Sylvie's hilarious. Like in her, I mean, I've never met her. I mean, I'm not just using an example, right? But I feel like I know her because of just the way she navigates these. And she's just an example, or you, Sylvia, are just an example. But the more you find your way of communicating through that the grading system is designed so that there's not just one way to show at the end of the semester that you've been part of this class and you've been trying to engage with physics. And the people that are engaging in this conversation right now, even though it's about grades, not physics, they are demonstrating that. Okay, but okay, cool. So, but thank you, I think. So on Marina's, unless she's talking about Marina's dog, on Marina's question, how's extra credit points? Yeah, okay. So that's another legitimate question. And again, at the risk, I mean, this is all in the syllabus. And anything I say now is true for all of you. Some of what I say is complicated and I overtalk all of it. The grading system is complicated. It is complicated, but it's not meant to be a hide the ball. It is explained in the syllabus, and it, whatever system I say about the grading, I mean, whatever I say about it is absolutely like true for every one of you. I mean, the rules are the same for every one of you. And also, I'm happy to expand on it privately with anybody at any time. And the underlying rule of thumb is it's designed to maximize your success if you try it all. But so now here's the specific answer to Marina's question. So the answer is no. The extra credit points don't count the same way at the same weight as the exam points, but yes, they do count as extra credit. So here's how it works, just quickly again. And again, I mean, I apologize to anybody who does already understand this, but it tends to be the case that people don't start really caring or like following the intricacies of this until the end when it matters. So here it is. In principle, in order to create the lecture portion of your grade, well, no, okay. In order to create your grade, I have to pause for 1 second. It's slightly different in 102. Hold on 1 second. Yes, okay. In order to create your grade, in principle, or excuse me, compute your grade, here's what happens. Principle, you have a midterm score when you eventually, you have a final, wait, someone's here, sorry. And do pay attention. And I think you all do want to hear this. You get a midterm score. You get a final exam score. You get a final average in lab, right? Like after all is said and done, all the work that you do with Mercedes, which is a ton, with Professor Talley, all that work that you did, all in the end is equivalent in effect to an exam grade. In effect, like it's like 1/3 of the whole class. Wait, no, that's not true. That's from the other class. Sorry, scratch that for a second. Scratch that part about the lab. Just scratch that for a second. In order to compute your lecture grade, in order to compute your lecture portion, and in this class, the lecture accounts for about 60% of the grade because you do a lot of, I was just confusing two classes. Your lab grade actually is worth almost, it's more like 40% of your whole grade. So put the lab aside for a second. In the lecture, you have the midterm, you have the final. In principle, they first get averaged together, whatever scores you get on each one. In principle, first of all, they get averaged together. Now, I'm going to tell you right now, because I've taken so long with your midterms, one thing that's going to happen in your class, whether I mentioned it or not, is that they're not going to be equally weighted. Whichever one you do better on is going to be weighted more. I'm just telling you that right now. So you take the two exam grades. One of them, whichever one you did better on, will be weighted more. So it'd be like 3-to-2 ratio, something like that. We average those grades together. Now you have your base raw exam average. Then all of the points that you accumulated from all of the game turn stuff and all of the showing video, showing avatar, being wrong, whatever. And some of you have put in a ton. And frankly, I mean, I know the person asking this question is one of those people. Some of you have put in a ton of those points. Some of you haven't. It's all optional, but all of those points that you've ever, and those of you who have put in a ton but still are waiting to get things back, you'll get them all back. They all come back. I promise. All of those points for all those extra credit things makes a huge pile in the, of like 200 points or something in some cases. What happens is at the end of the semester, when I'm going down to sit down to do the grades, I come up with a scaling factor that is the same for every student. It's different every semester, so I can't tell it to you until the end, but it's the same for every student. I come up with a scaling factor such as, let's say, 10. Let's say like 20. If the scaling factor is 20, that means I would take all those 200 points that, for example, Marina has accumulated. I would take her 200 points. I would divide by 20, and that makes 10. I would take the 10 points and add it to her exam average. Now, actually, I would add it to her exam average. And that now she has a new grade. Then for each and every person in the class, I reserve the right, or they have the right to get one more point for class citizenship, class engagement, so you either get 0 or you get one more extra point for being an engaged citizen of the class, which essentially anybody who's listening to me right now or anybody whose name I know at all is such a person. So you have your exam average, where the better of the two exams is weighted more. Then you get all these extra points added. So they're not literally, they are extra points, but they were scaled down. So to answer Marina's original question, and let me make the number even slightly more realistic. Let's say in the case of Marina, she might have had 240 points accumulated. I'm making up numbers, but they're actually not crazily unrealistic. And let's say the scaling factor, like I said, was 20. So I would divide 240 by 20 and I would get 12. Okay. That would mean that 12 points gets added to her exam average. And then, because she's even asking a question right now, and you all know who she is and you all know her dog, like then she probably does qualify for that extra 1 point. So her final grade in lecture would be the average of her two exams with the better one counting more, plus 12 points, plus the extra point. That would be her grade in this class. And that would be counting for 60% of the whole thing. Then I take Mercedes's grades, the final grade for Mercedes, that counts for 40% holding, just because that's the distribution that we decided a long time ago for 102, because you do so much lab work, like the lab really needs to count, like a lot. And we put those together, and that's your final grade. Now, as long as I'm talking about this, let me dwell for one more second, make it super clear. First of all, I'm saying as an example that the scaling factor would be like 20. Which would mean that if Marina had 240 points accumulated, I would divide, she would have 12 extra points added to her average. Anybody else in the room would also have their points divided by 20. So some people would have also 12 added to theirs. Some people would have 7. Nobody would be penalized at all by that. So if they rock the exams, they don't even care. They don't need any of this, whatever. But in the case of that example of 12, notice 12 is a lot. You all know 12 is a lot. 12 makes the difference between a B minus and a solid A, or a C minus and a solid B, etc. Right? You might be asking yourself, is that even realistic? Like, is that actually what happens? Does he actually add like 12? Yes, it is a typical number. And again, not to call, but like Marina does a lot of those. I mean, I know that. The number probably is something like 12 in her case. If you never do them, it wouldn't be a number like 12. But 12 is a little high, but it's not atypical. The average is usually around 9 or 8. And that's how I come up with the scaling factor. I come up with a scaling factor that such that the typical people in the typical class who are doing a typical amount of trying to work and trying to do these extra points will necessarily have a grade that's like 2 half grades higher than what their exams seem to indicate. That is the idea of it. So I'm taking a long time to explain this again, and I apologize, but just because I know we're all nervous at the end of the semester, what I'm trying to make clear is, no, those extra points don't literally count point for point as exam points, but they're scaled so that at the end of the day, what you get on your exam is probably 2 half grades lower than what's going to end up on your transcript, because that is how much they count. They're there to make sure that you are not just judged by your exam at the end of the day, because you only did 1 or 2 exams and you have to wait this long to get them back. But you've been with me all semester doing all this work. So 12 is a typical number. Sometimes they're as high as 14. They're not usually much higher than that. And sometimes, for different people, they might be as low as 6 or whatever. But that is more or less a realistic example of what the homework points do. And again, the reason I have to spend so long explaining it, sorry, but the reason I can't literally, and the reason, so if any one of you was worried about your grade and came to me to talk about it, we would talk. But I wouldn't be able to give you exact numbers. I would give you projections, because I don't know what that scaling factor is literally until everything is said and done. The scaling factor is the background mechanism by virtue of which I use all of your homework and all your extra work as a lever to weight your grades appropriately. I mean, it's like a curve, but in 1,000 ways, it's not strictly a curve. It's different, but it acts like a curve in that it means that your exam score is not your final grade. How much not, we don't know until the end, until I've seen all the numbers. Okay, sorry, but I hope, but again, if you didn't get all of that, or if I'm yelling and that's freaking you out, the message is that if you give me anything to work with, and it's still not too late, if you've been giving me anything to work with, the system is designed to take the clay that you give me and have that be sculpted fairly into a high grade. I don't care what kind of clay it is. If you give me clay, it'll find itself sculpted into an appropriately high grade. And I mean appropriately, like I don't think it's a gift. I just think it's a recognition of different ways that people have of engaging in a course. If you don't, and the other flip side, again, it's probably too late for me to say this, but the flip side is it all works and it's all fair because every single semester there are just enough people that disengaged just enough or didn't engage just enough that they actually do end up with poor grades that justifies the whole system and means that everybody who does get a good grade is not getting a gift. Everybody who gets a good grade in this class means they did the class as it was intended to be done. Okay, so I hope, so please just know, so if you just do stuff, it'll work out is the idea. Okay, sorry.
Thank you for the clarification, Professor.
Oh, okay, cool. Thank you. So it made sense. Okay, thank you. And thank you for being with us all the time.
Yes, it did. Because I remember you saying you were going to come up with the scale at the end of the semester. I remember you saying that. But I guess my question was more along the lines of like, did you come up with it? But then you actually went into it. So like now I know like you're still like in the process of that.
Right.
Of coming up with the scale.
Right. And not because, and literally because it gets determined once all the other grades land. Yeah. Because it's like you got it. So yes, cool. Oh, now there's a random question in the direct chat too. Also very fair. Someone in direct chat is asking, do I give A pluses or do I only give A's? Totally fair. There are no A pluses at John Jay. I've faced this problem before. I have mixed feelings about this, but no matter what I think, or no matter what I might want to do, they're literally just, unless I've changed something that I don't know about. Believe there have been times when I wanted people to get A pluses, but no, the highest grade that can land on your transcript, as far as I know, the highest grade that is available to me is A. Right. No, it's there's a lot of weird. I mean, don't get me. But yes, but I think, unless you've ever had a different experience, that's my understanding. Yeah. I mean, I don't know what to say. I mean, the other thing that surprises me is I'm surprised that. Well, I don't know what it says that you're learning that from me. I'm not sure what that says that we're like realizing this right now in the middle of this class, but like, yeah, that is the case.
I actually tried to get the dean to change the grading scale. Like I tried to ask her, can you incorporate A plus? Because I know at City College they have A plus. Right. And I said, well, that's a CUNY, so why don't we have A plus? So I tried, but she didn't want to change it.
Right. And I don't know what the reasoning is. And you're absolutely right that it is interesting how the different CUNY schools definitely have different nuances to their grading system. And look, and if I'm not careful, I could go, I mean, yes, you're right. And it is, and good luck ever trying to fight City Hall on that. I mean, like, right. You could get a whole, union of faculty to march and not that they would, but yes, I imagine it wasn't a very satisfying experience for you as one student going in and trying to get that changed. But yes, I mean, there's also the very interesting thing. Wait, should I talk about this on a record? It's also true that we all know, and I hope you guys know, especially if you're still going to be, that John Jay, it's not all of the schools that have this, but at John Jay, should I say that? Okay, I don't want to get into this discussion right now. So I'm going to say something, if you know what I'm talking about, let's just all secretly sympathize with each other and move on. If you don't know what I'm talking about, you might want to ask me later in a text or an email or another student, but you do understand that in most circumstances, if it came to it, how can I put this? I'll put it this way. If I were the way the policy is written at John Jay these days, if I were a student at John Jay, I'd rather see an F on my transcript than a D. I think you're all aware of that, right? Like that. Okay. Just if you don't know what I'm talking about, you do want to, and you ever think you're in jeopardy of any of those kind of grades. If you think you're in jeopardy of either of those grades in this course, we should talk. And, if I think you're in jeopardy, we will talk. But just in general, if you think you're in jeopardy of either of those two grades, please be aware of the exact implications of both those grades, because the implications are unexpected, perhaps. anyway, that's okay. All right, let's do some physics. Oh, sorry. Any other? Shall we do some physics? Okay, I think I'm going to try to do some physics. If there's more, put it in the chat. I mean, for real. But okay, here we go. Now, what I want to try to do is get my board working. Now, what I'm ideally going to do today, I always say this, and like never, ideally I have two different things I'd like to do. And one, I do want to explain things, then I want to be more participatory with you. I want to talk about the lab you just did. And I know if I'm not careful, that's not going to happen. But I can't do that first. I can't talk to you about your lab first because it's already the material's a little bit confusing about how you're doing one thing in lab and one thing here. So I need to stay on track with the sequence of the material. So first I need to explain something that goes back to all this electricity stuff. Like we were talking about last week, right? I've been trying to sort of catch up and put theoretical grounding in all this electricity business that you had been doing in the lab. Okay, so bear with me. So I'm going to stay on the electricity topic here for one more hour or something. And then ideally, I'd like to shift gears and talk to you about the lab you just did. I know that went pat, you know, that's one of your last labs, if not your last. But first we have to, so if you want to send me a reminder or something at 6 o'clock, feel free. But here we go. With what I specifically want to talk about, I want to go back to talking about electrostatic fields and specifically field line diagrams. Okay, I believe, and you're going to correct me if I'm wrong. I'm going to be, for the next hour or so, maybe more, I'm going to be switching back and forth between this whiteboard right here, you know, where I'm taking notes, versus images from Google that we were looking at, that I believe we were looking at last time. So in fact, I'm going to start with that right now. I want to correct me if I'm wrong, but when we ended last time, were we not briefly looking at pictures like this and briefly discussing pictures like this of electric field line diagrams? Is this from, am I right that we ended last class looking at pictures like this, or have you never seen a picture like this before?
I think that you had hand-drawn some that were similar to this, but I don't think we saw pictures.
Oh, okay. So we ended on the hand-drawn. Okay, that's very possible, actually. All right. Thank you for the clarification. Okay. Okay. So let me back up for a second. Okay. Right. Thank you. I believe that's clarifying. Okay. So these two pictures that you're looking at right now are two examples of two different electric field. Well, they're two different examples of two different electric fields. Particularly, they are two different examples of two different electric field line diagrams. Okay, the one on the left, I believe, is like the one that I hand drew for you last time. The one on the left is the simplest, most elemental, most fundamental field situation that we can imagine or that we talk about. The one on the left is a line diagram of the electric field produced by a positive point source. Okay, remember again that source is the thing creating field. Field is force waiting to happen. Mathematically, specifically, field is force per charge. I'll probably say that over and over again, and I'll hopefully write it over and over again, but that's what it is. Field is force per charge. If force is measured in newtons, then field is measured in newtons per coulomb. The idea behind it, again, I'm just trying to be sort of conceptual for a moment here. The idea is that any force in the world, any and every force that you ever imagine, is always an interaction between two thingy things, two material, tangible, discrete objects, right? So a force is like, I push you or I pull you. Any kind of force is like that. Specifically, the gravitational force is I am a point mass. I pull on you if you are a point mass. Or every bit of mass gravitationally pulls on every other bit of mass, every point. Similarly, the electrostatic force, the one that we're really concerned with right now the one that we're concerned with in this class, the electrostatic force is every bit of charge pulls or pushes on every other bit or point of charge in the universe. Okay, so force is always what one thing does to another. But some of those forces are special, remember. We went bananas about this concept last time. Some forces, like the gravitational force, like the electrostatic force, seem to occur through empty space without touching, right? And more specifically, they seem to act through empty space without touching, but in a manner that is quantitatively precisely determined by measurements describing the two objects that are not touching each other. So like again, like with the electrostatic force, we say that if there's a bunch of protons over here, a certain distance away from a bunch of electrons over there, what we believe is that the protons are pulling the electrons with a number of newtons, with an amount of force that is precisely determined by exactly how many protons are here and how many electrons are over here and how far apart they are, right? This is the thing I went crazy with last time. And that's really like a bizarre, it's like a very kind of hard thing to believe, especially when you consider that means if the electrons start getting closer to the protons seem to adjust the strength of their pull. They adjust the number of newtons being exerted in accordance with the new location of the electrons. Or if the number of electrons were to change, like if there were 10 electrons over here and now there's 5 electrons over here, the protons pull with a new amount of force. So somehow protons over here are always somehow accessing the information describing electrons over here. Or let me say it the other way around. The electrons over here are somehow always knowing or accessing precisely how many protons are over here and how far away they are. So what we say is, okay, if that's true, if somehow the information of everything that's going on, if somehow the information of describing things in space, if somehow that information is always everywhere in space, then let's start talking about that information regardless of what it's doing. Like, let's talk about the information describing protons over here. Let's talk about that information even before electrons wind up experiencing it. Like, the information seems to be there whether or not it's doing something to, I'm going to say it one last time, the information describing sources seems to be there whether or not the information has yet to do anything to receivers. So from here on in, we talk about field, right? Just again, to sort of remind you or to try to tell you what these pictures are all about. If force is what a proton does to an electron, field is what a proton does to space. Field is what a proton does to this location in space before an electron is even there to experience it. What the field is all of the vital stats of the proton. It's the number of protons that are over here, and it's the location, like exactly how far and in what direction the proton is from any given point in space. It's all that information bundled up together into like a little vector in our imagination. And so what we say now is anytime there, so whatever charges are causing the field are called source charges. And the field is a representation, or the field is the medium or the repository of the force per any charge that could be or would be or might be located at any given point in space. So whatever, it's bottom line, whatever's causing the field, we call the source. And whatever might experience the field, we call the test. We call it a test because it doesn't actually have to be there for the field to be there. So this picture, okay, so this picture to the left is the field line picture associated or drawn for one positive point source of charge. It's got these lines coming out. It's got 8 lines. Oh, excuse me. Thank you. Okay, my son just said cringe. Yes, that is one thing in the electrostatic field definitely are. They are cringe. Okay. The left represents the field lines. Oh, excuse me. The left is a picture of field lines that represent the field due to a point source. What the lines are trying to tell us is for any given point in space that you might consider, the lines are telling us how hard and in what direction a positive 1 Coulomb of test charge would be pushed or pulled if it were found at that location. Let me say that again. And I'm going to switch boards a second because I know this is getting all, I'm just like talking. The field lines are meant to show you for at any given point in space, how hard and in what direction you'd be pushed or pulled by the source if you were a 1 Coulomb of positive test charge located at that spot. So the field lines are meant to show magnitude and direction of force waiting to happen. The field line picture to the right is much more intricate, as you can see, much more intricate. What's going on with the field line picture to the right? The field line picture to the right is the field lines, is the field situation produced by what we call a dipole, a point source of positive located in one place nearby another point source of negative charge. In other words, the positive and the negative in this picture to the right, in this picture B, the positive and negative are both creating field. They're both pushing and pulling on the universe. And all the lines, this picture of lines is meant to show us what's happening everywhere in the universe due to that pair of point sources. I'm going to get more and more specific with this, for like an hour, believe it or not. I mean, I'll make it more concrete. But the first thing I want to say about this picture to the right, we're going to break down this picture and learn how to interpret it and learn how it got drawn. But the first thing I want to say about this picture to the right is it's not, all those arrows are not trying to tell you how the negative might move toward the positive. They're not. It looks like that, perhaps. Or it might look like all these lines are trying to tell you how the negative is being attracted to the positive, or how the positive is being attracted to the negative. That's not what the picture is about at all. We're supposed to assume that the positive and negative are like fixed. They are things that are sitting in the lab, or they are nuclei that are sitting somewhere in the universe. They're just sitting there. And the lines are their combined effect on the space around them. So the lines are meant to tell us what would happen to a third party. The lines are meant to tell us what would happen if you stuck 1 Coulomb of positive test charge, say over here somewhere. Then if you know how to read the lines, what you'd be finding out is what would happen to a 1 Coulomb of positive test charge over here due to the presence of the dipole down below it. So according to this picture, if I had 1 Coulomb of positive test charge over here, it would be shoved to the right, as you can see by that arrowhead, and it would be shoved a pretty weak amount, not very much. It turns out, if I went down here, it turns out, if I know how to read this diagram, I would find that a positive 1 Coulomb of test charge would be shoved to the right, but by a very strong amount. And when I say strong or weak, I mean the number of newtons with which it would be pushed in effect, each of these locations, each of these arrows is telling you the number of newtons that every 1 coulomb of charge would experience, and each one of the arrows is telling you in what directions the newtons would be pushing or pulling. Now that's the basic idea behind this. The more complicated pattern that we assemble source charges in, the more complicated the E field lines get. Now I'm going to go off. What I'm going to start doing is showing you exactly how to read these by showing you actually how they're drawn in a minute. But I first just want to scroll. Well, yeah, no, actually, I'm going to switch screens now. I'm going to make this more concrete. Okay, so is there something in the chat? Okay, so first, I'm going to give you what's going to happen now for a little while. I'm going to give you the 7 rules, a set of 7 rules for creating field line diagrams, which in turn, if you understand the rules, if we walk through these rules, you'll have a better understanding of how to read diagrams, and you'll know what they're saying. I'm not expecting that we don't have that much time left in the semester. Obviously, I'm not expecting that we're going to draw 1 million diagrams together. I'm not trying to make any of us like experts in drawing these diagrams, but I am trying to get across to you. Well, but I do want us to understand these diagrams well enough to at least to know how to read them. And ultimately, the reason I want that, we're going to spend some time on these diagrams because they are our way of picturing. They're our best way at this point as physicists. They are our model, or our mental model, our mental representation for how information is distributed and contained and transmitted throughout space. So every claim that I'm going to make from here on in about a picture, please remember, I'm not just talking about pictures just because I think they're pretty pictures. These pictures are strict representational computational tools, much like graphs or vectors or free body diagrams or maps. Like, when you're lost in the world, you take out a map, or you take out GPS or whatever, but you take out a map and you start making decisions based on that map, because you really, or once upon a time we did anyway, because we really take maps seriously. Like, we really sort of trust that maps are drawn to scale and accurately enough that if the map tells us to do something, we actually think that means something in reality. That's what these pictures are. They are maps to the way information is distributed in reality. So it's really, and they show things that I just cannot say otherwise about information. So we're gonna go through these. The goal of today is to learn how to draw one of these pictures, even though, to be honest, I'm not gonna ask you ever to actually draw that many of them. But here we go. The first, sorry, things are happening on my screen. Hold on, let me think for a second. Yeah, okay. So here's rules for creating E-field line diagrams. And at each rule I give you, I'm going to flip back and forth between the pictures and show you examples. So the first thing you do when you're drawing or constructing or picturing a field line diagram in your mind is you choose a scaling factor. For example, you say, I'm going to do 8 field lines for every 1 coulomb of source charge. Remember, source means whatever charge is creating the field for each 1 coulomb of source charge. So you choose a scaling factor, and then you commit to maintaining that scaling factor consistently throughout your drawings. And also you commit to applying that scaling factor in as symmetric a fashion as you possibly can. What I mean by that is this. So you obey it consistently and symmetrically. I'm going to flip the board again and show you what I mean. If you look at the left-hand picture, right, the simplest possible picture, there indeed, we picked a scaling factor of 8. Like, if we assume that point source, that positive, is meant to be 1 coulomb of charge, 1 coulomb of charge, which again, by the way, sidebar, I think I explained this last time. Remember, every time I say 1 coulomb of charge, excuse me, every time I say 1 coulomb of positive point charge, what I'm really picturing is like 16 quintillion protons jammed together into a Euclidean dot. Like this is all very, very, in a way, hard to picture, which is why we need the simplest possible representation we can come up with for helping us picture it. But when I say a point source of 1 coulomb, what I mean is like 16 quintillion protons jammed together into as small a volume as is possible. That's what so, but imagine I have that, but that is possible. It's hard to picture, but it's totally a real thing. So imagine I have 1 coulomb of positive charge, located in the lab. I say to myself, okay, for every 1 coulomb of charge, I'm going to draw 8 field lines from here on in. That means I'm going to draw 8 lines coming out of this dot as symmetrically as possible. In fact, that's why I picked the number 8. It's not a coincidence, and it's fairly common. That way I could draw 1 going up, 1 going down, 1 going left, 1 going right, and then make an X with the remaining 4. I could have chosen 4. That'd be probably fine. And I could choose 16. I could choose 5, but that's like harder to do symmetrically. But 8 is like a reasonable number. It's just enough lines to show the pattern. Right. And remember, that's what I'm doing here is I'm showing a pattern. The whole idea is that there's field lines everywhere in space. We draw just enough to indicate the arrangement. So 1 point source pushes out. It creates field that pushes out equally, symmetrically in all directions in space. Why does it push? Because the field is a representation or a consideration of what force would be exerted on a test charge of positive 1 coulomb. So this is all a picture of what would happen if a positive 1 coulomb of receiving charge were placed somewhere in that picture, the picture to the left. Positive would be pushed out by a source positive. If my source happened to have been negative, these lines would go in, but it's positive, so they go out, right? So what we're saying is anywhere you are in the region of this positive, you'd get shoved out with a certain number of newtons in a certain direction. Okay, so I'm over talking. So rule number 1 is you choose a scaling factor. If both of these pictures, A and B, are meant to capture 2 different regions of one lab or something, or 2 different regions of outer space, then they're following the same scaling factor. So if you look over in picture B, you notice the positive there has like 16 lines coming out of it as symmetrically as possible. It has 16 lines coming out of it. So that right away tells us, oh, that positive over there in picture B, that must be like 2 coulombs of charge. Okay, that's the idea, is that for every coulomb of charge, you're adding that many more lines, but you always add them as symmetrically as possible. So that's rule number 1. So, okay, and so then if I had just a half coulomb of charge, then I would just have 4 lines coming out of it, but as symmetrically as possible. So the first thing you do is you choose a scaling factor, and then you start drawing lines according to that scaling factor as symmetrically as you can. Now back, so that's rule number 1. Wait, there are things happening in the chat, I think. Wait, hold on a second. Hold on. Or is this old? I can't. Oh, okay. That's just because, okay, sorry, because it's 2 devices. Okay, so now we go back to rule number 2. All right, so now here's about to be rule number 2. Rule 2. Okay, now rule number 2 says every field line must either start at a positive source. Hold on a second. Hold on. You can ignore the parentheses for a moment, but Okay, every field line. Remember we said a minute ago, field lines go out of positives and field lines come into negatives, because again, what the field lines are indicating is what would happen or what will happen to a positive test charge. Okay, so they got to come out of positives and they got to go into negatives. But is that the only thing they can do? Well, yes and no. Every single field line you ever draw has to either come out of a positive or come in from infinity. And every field line has to either land at a negative or land nowhere and go off to infinity. Okay, so partly what this is a way of saying is when you sit down to draw a field line diagram, or you sit down to understand a field line diagram, after you've chosen the scaling factor, then what you do is basically you walk over to your whatever positive charges you're seeing in the picture, and you start making lines come out of the positive. And you go and you walk over to the negative and you start making lines coming into the negative. Now, if there's if they're equal charges, every line that started the positive will land on the negative. Like they'll have a home in both places, a source and a sink. But sometimes there might be leftover lines. Like sometimes you might have 2 coulombs of positive charge and 1 coulomb of negative charge. So maybe there's 16 lines coming out of the positive, but there's only 8 lines going into the negative. So there's 8 extra lines. What happens to them? They go off to infinity. They go off to infinity. As opposed to what? Or what does that mean? It means we understand that they're never ending. It means as opposed to ending somewhere in the middle of the page. What this is all saying here, when I say so this is 2 rules. Every field line must either start at a positive or come in from infinity. And then rule number 3, every field line must either end at a negative or go off to infinity. If you were thinking, when I first heard this, it made no sense to me. Like I still remember when I first heard this and it made no sense. First of all, I didn't know what they meant by infinity. But second of all, I was like, once I kind of knew they meant, okay, go off the edge of the page, then I was like, well, as opposed to what? What else would a line do? I don't even understand what you're saying. What they're saying, what I'm saying here is what lines don't ever do is start or stop spontaneously in the middle of the page. This is actually bizarrely important. What I'm saying is these lines have arrows on them. They are indicating direction, but they're not vectors. They don't have tips and tails. These field lines do not have tails or tips. They're not arrows with particular lengths sitting. They don't start or stop in space. So I'm going to switch screens again. So much so that if you look back at these pictures, sorry, hold on a second. If you look at picture B, you notice that a lot of add picture A, but specifically if you look at picture B, you notice that there are all these arrowheads in there indicating direction. Like I think direction of line is pretty clear. But you notice that the arrows are like the arrow heads are drawn intermittently along the line. When they're not tips, the line doesn't end when the arrowhead comes. That's really strongly trying to reinforce that these things are not vectors. And you see like some lines that are coming out of the positive that go up and bend over and then come down into the negative. But then there's other lines that also have arrowheads in the middle of them that are going up to the page. And then what I'm trying to say is that we're supposed to understand that every one of those lines that can come up and bend over and continue the pattern and come down and hit the negative does. But any line that can't come back around and hit a negative goes on forever. So it doesn't stop at any particular point. Therefore, the bottom line of everything I'm trying to say is there's nothing to be inferred from the length of any given field line. All field lines are either infinite in length or they just happen to be some length that gets them from the positive to the negative, and they're as long as they need to be to smoothly get from a negative, from a positive to a negative. So the length of a field line does not mean anything, unlike vectors, where the length of the vector tells you the magnitude of the vector quantity. Okay, so that's rule number 2 and 3, is that the lines go from positive to negative, or, oh, and there goes my board, or they go from or to infinity. I'm trying to go back to the board now. Okay, so that's rules 2 and 3. Here comes rule 4. Now this becomes very important. This is a little, I'm going to read it out loud. You can write it or copy it the way you see it, and then I'm going to try to explain it because it's a little more. All right, well, I'll read it out loud first of all. It says, at a point on the page, direction of field is represented by tangent to field. So you could say by line tangent. Oh. Yeah, by the line tangent to field line at that point. So at a point on the page, direction of field is represented by the line tangent to field line at that point. And then it says magnitude of field in space is represented by density of lines per unit area on the page. Okay, that is a mouthful. I'll give you a second to copy it down, please, or possibly, but then I'm going to show you what I'm talking about on the picture. But the first thing I'm saying while you copy down is please remember at all times, the purpose of a field line diagram is to indicate magnitude and direction of force per charge acting at any and every given point in space. Field lines are meant to show magnitude and direction of field at every point in space. So field lines are meant to show the kind of information that once upon a time we used vectors for. Field lines are meant to show what we could continue to use vectors for, but and we can continue to picture field as a bunch of vectors in space, and that is what it is. The field, due to some bunch of charge over here, is a bunch of vectors everywhere in space. Everywhere in space you look, there's a little arrow, you could say, showing the magnitude and the direction of the force waiting to be exerted on each coulomb of positive charge. However, we're not drawing vectors anymore. We're sewing up all the vectors and drawing lines to simplify things because this is already complicated enough and we would have way too many vectors. So we're using lines to try to convey the information that vectors are meant to convey. The two types of information are direction and magnitude. So what we need to see now is, well, how are direction and magnitude conveyed by these lines? So I'm going to show you. I'm going to switch the screen. The first thing we're saying is that direction of field is indicated by direction or slope of tangent line to field line. Okay, what do I mean? I mean, say if you could see my hovering mouse, like say my mouse, can you see? Yeah, I think you can. Like the black mouse is like hovering like right around here. Say I went to right here. I want to know, so I picked that location and I want to know what's the field doing at that location. Meaning, if I pictured 1 coulomb of positive charge at that location, in what direction would it be pushed? And how much would it be pushed? Like, that's what I'm trying to ask. So as far as direction, well, strictly speaking, the direction you'd be pushed right here is if you pictured a line tangent. If you pictured a line, can I do this? Maybe I can do this. Hold on one second. I don't know if this is going to be worth it, but if I pictured a line, course, it's the wrong color, but if I picture the line. It's totally not worth it, but maybe it is. Okay, there's a point. There's a black point right there. If I wanted to know the direction of field right at that point, I would picture the line tangent to the field line at that point, and the slope of the tangent line would be the direction that the field is pointing at that point. Now, you might say, well, okay, why, Yaverbaum, really? Like, really? Like, I get it. Like, you're just saying the direction of the field line is the direction of the field. Like, why do you have to say all this crap about tangent lines? Like, really? Well, yes. And no, on the one hand, yes, if you're getting that the basic point I'm making is just the direction, the slope of the field line is the direction of the field, then yes, you are getting what I'm saying. But why am I introducing this whole tangent line business? Because you notice the field lines are curved. The field lines are often curved. To be curved means to change your direction at every point, right? To be curved means that your slope is different at every point. What I want to emphasize to you is the direction that something would be forced at a point is the direction of the line at that point. So if I put a positive test charge at the dot, like right there, in my picture, it would, right at that dot, it'd be forced down along the tangent line. But we use tangent lines to express slope at points. And the reason we use tangent lines is a recognition that if I go far enough down the line, or if I go like over here, if I look here at this dot, if I were to go to that dot, right, the tangent line is very different there. Even though it's the same field line, the tangent line is very different. I guess I can use arrows. Oh, that's cool. I should have done that before. All right. Right. So the tangent line is very different at the top. So what I'm really trying to say with the tangent line thing is at every given moment, at every given location, these field lines are indicating a different direction. So the direction is the direction that a test charge would be pushed or pulled and thereby accelerated in that direction. So what I'm really trying to emphasize here in the long run is, and you might even want to write down, test charges do not travel along field lines. These field lines are not highways. They're not indicating paths. They're not indicating what direction your velocity would be in. If you're a positive test charge, you don't move along lines. At any given moment, if you're on one line, that line shoves you in a certain direction instantaneously, shoves you along a tangent line. And you'll then, therefore, you'll land on a different line. And then the line shoves you in a different direction and you land on a different line. So I don't want you to think, so that's why I'm saying the whole business about tangent line. The direction of force per charge, the direction of field at any one location is the direction of the line tangent to the field at that point. That's direction. Now, magnitude, if these were vectors, magnitude would be represented by the length of the vectors. But I was just like screaming and screaming 5 minutes ago that there aren't lengths anymore. These lines don't have lengths. They either go on to infinity or they just go to the negative charge and then they're as long as they need to be to do that. So we can't use length to indicate magnitude of field. So how do we tell, and I'm warning, distant early warning, I'm about to turn a question to you guys. I'm about to ask you something. So this would be a good moment to tune in if by chance you might have been thinking about something else. I'm going to remind you that the field line is meant to convey direction, and magnitude of field at every point in space. The field line diagram is meant to show how hard and in what direction any bit of test charge would be pushed or pulled due to the source charges at the center of this picture, right? So it's meant to convey direction and magnitude. The direction, I'm saying, is indicated by the arrows and the tangent lines on the field lines. But my question to you is, and I'm going to ask this like 4 different ways, possibly, if I need to. My question is, how can you look at this diagram and tell where the field is strong and where the field is weak? And you can look at this diagram and you can tell where the field is comparatively strong, where the magnitude of force per charge is comparatively strong. And you can tell, looking at this picture, picture B, you can tell where the field is meant to be weak. So my question is, how? And I'm going to wait till I get 3 answers in the chat, in the private chat. And I don't care if they're right or wrong, but this is like a come together moment for all of us. I'll repeat the question as many times as I have to. I'm asking, but I do want answers in the private chat, please, or the direct chat. I hate saying private, it's so weird. In the direct chat, I'm asking, what aspect of this picture of a field line, what aspect of it, what property indicates strength, magnitude, intensity of field? Like an example would be length of arrow, but that's not the right answer because we've already eliminated that. Like that for vectors, length of arrow indicates strength of field, but we're in field lines now. So what is it about these lines that's telling us how strong the field is? I'm going to say it again. So again, I'm just yammering until I get answers in the chat here. I'm looking for answers in the chat, or I'm looking for something in the chat like, wait, could you repeat the question? Or something in the chat like, I don't get the, oh my God, 4 things just happened in the chat. That's amazing. Hold on. And I'm totally going to look. I'm just going to repeat the question one more time because now people clearly are paying attention. The question is, how can you tell, looking at this picture, where the field is supposed to be strong and where the field is weak? Wow, there's 5 things in the chat. How much do I love this class? 5, that's how much. No, 6. I love this class. 6 million Googleplex. God, do I love this class. Okay. Oh, wow. Okay, so I'm looking at the chat. Wait, the chat is frozen. Why is the chat frozen? I'm seeing good answers in the chat, but it is frozen. Hold on 1 second. By the way, I can only see some of the answers because something is frozen right now. It might be because I'm trying to, hold on, I may have to stop the share. Stop the share. Stop sharing. Just take turns. Okay. Yeah, that did it. So I'm looking at the chat, but I'm also can tell you right away, even if some of the answers are wrong, I don't care. And by the way, this is another opportunity. If you are concerned about points, if you heard that whole discussion with Marina about how the points work, I'm still totally taking all of those game participation portals, and not the daily turns, but all the other ones they're all optional, but they're still all fair game. If you've ever used the YouTube channel, you can put in that portal for points. If you subscribe, whatever. If today you participate, you put in an answer, put it in the portal for answers. If you're about to find out that maybe your answer was wrong, do not be ashamed of yourself. Enter your wrong answer in my favorite portal of all, the portal for wrong answers. Literally, I want that on my tombstone that I did that. But now I'm looking in the chat and I can already tell some of the answers are more right than others, but all of the answers in the chat are definitely indicating that you're understanding the question, which I really appreciate. So now I'm going to look at it very specifically. Okay. So I'm looking at the chat. Okay. Awesome. Okay. Awesome. I'm just reading them to myself. Maybe I should, maybe I shouldn't, but hold on. I'm seeing a lot of really cool answers. Well, I'll sort of read them out loud. Okay. I'm not going to read names, but I see. So remember, again, the question is, how can you tell from the picture, looking at the line? And I kind of do mean by looking at the lines, what aspect of the lines indicates strength of field, or in other words, number of newtons per coulomb that's happening. So I'll just read it out loud. So I see how many arrows are surrounding the plus or the minus. I see density of the field lines indicates magnitude of field. In other words, the strongest field is in the center between the 2 charges. The weakest, the lowest magnitude is in the longer arched field lines at the top. I'm reading out loud, but I'm reading in a funny order. Then I see the charges, meaning I guess the strength of the charges. I see how many lines are connected. So like how many of them there are indicates strength of field. I see, oh, if the line is solid or dashed, that's a really good thought. Are the lines solid or dashed? I think all the lines are solid though, actually. That's an interesting, okay, I'll keep reading. And then I see the arrows. Okay. Oh, interesting. Okay. So one person put the arrows and then another. Wait a minute. Wait a minute. Sorry. One person put the arrows and I want to address that. And then another person says, did that carrot thing, which I think in your generation means I agree with the person before me, or like facts or whatever. Or maybe that's the double carrot thing. But I thought the carrot thing means like I agree with the person before me. And the only reason I'm going, wait a minute, is how it looks normal on my side, but how would a person agree with somebody else in direct chat? Something sus is going on here. But whether or not. So one person said something about the arrows, and someone said, yes, the arrows show it's strong, like the field is weaker as the arrows move away from the two charges. That is very interesting. I'll respond to both of those in a minute. But then I see how long the line is. Then I see, a lot of you are participating. I really appreciate it. This is good. Then I see, I would predict that the lines closest together represent a stronger force going on, where therefore field, whereas the ones farther apart are weaker. All of this is very good and very thoughtful, and again shows that you understand the question. And then someone saying like specifically, is the stuff stronger near the positive area of charge? Maybe. And then someone wrote maybe the distance between the arrows, which would mean distance between the lines. Okay, this is great. There's a lot of different answers here. And you notice just about all of these answers, they're different. And some are more right than others, frankly. And I'll address that. But you notice, that all of these answers, they are doing what I'm asking you to do. All of them are seeking out some property, some indication in the picture that actually tells us how strong the field is. Now, what I want to address first is there's one answer that was sort of interesting that came up like 3 times or something, totally fair, totally showed that the question was understood, but I do want to, but it is not right. I just want to address it. When people were talking about the arrows, like the direction of the arrows, and I'm going to reshare the screen. When people were talking about that it might be like the direction of the arrows, or saying things like, okay, as like wherever the arrows are pointing, as you're getting farther and farther, someone was saying something like that the arrows are pointing from the positive to the negative, so the field is getting weaker as you get closer to the negative. Or I might have misinterpreted that. But I want to reinforce again, that's very thoughtful, like that could make sense, but it's not the case. 2 reasons. One, the arrows are all about direction. Direction is one type of information. What right now we're focusing on is size, magnitude, strength. We always do want to keep those two types of information like separated in our mind. So the arrowheads, whatever arrowheads you're seeing, they're all about what way you'd be pushed or pulled. If you were anywhere in this space, what way you would be pushed as the net effect of the 2 sources in the middle of the page. But what I'm asking now is, and so again, I want to reinforce the picture is not showing you what the positive is doing to the negative. We're actually assuming that even if the positive wants to be doing something to the negative, it can't. They're fixed there. What we're looking at is the combined effect of the positive and negative on the space surrounding them. So the way magnitude is indicated, and a lot of you said the following in a lot of different ways, the way we read magnitude off the page is by the number of how close the lines are together, the density of the lines, as some of you said, the density. Oh, and in fact, I guess I even gave you this in the notes, I guess, before. So I guess it's partly like just how well are we following these notes. But yes, the density of lines per unit area indicates the strength of the field in that area. So like at least two people said in the chat, if you hover, if you look down here, if you look down here, the field is really strong because you're like really close to this positive who's pushing you to the right, but you're also really close to this negative who's pulling you to the right. So right here in this region, all the effects of the positive are reinforcing the effects of the negative. And in a way, the positive is depositing a rightward pointing vector right there in the center. And the negative is depositing another rightward pointing vector there. So you got two vectors that are both pointing to the right, both of equal size in effect. So they reinforce each other. So they make this really strong force pointing to the right. So there's a lot of arrows. They're all bundled together, all really dense in that region. The density of the lines, the crowdedness, the number of lines per unit area is indicating strong field, Luke. Whereas if you go up here, you're much farther away from the positive and you're farther away from the negative. So you're getting, they are reinforcing each other. The positive is pushing you up and to the right. The negative is pulling you down and to the right. So the ups are canceling the downs, and you have a leftover effect of rightward push up at the top, but it's not as strong as the rightward push down here because you're so far away from the plus and the minus. And this whole thing is, remember, KQ over R squared. This whole idea is that the field is directly proportional to strength of charge, but inversely proportional to the square of distance away from the charge. So bottom line, what I'm saying is, and again, many people said many different things. Not everything was exactly right, but hopefully you're all getting it. It's the number of lines per unit area on the page indicates strength or magnitude of field in the space represented by that page. Okay, now there's something in the chat. So someone wrote in the chat, interesting question. Is it possible to calculate how far each positive and negative charge is from each other? Interesting question. The positive and negative charges, how far away they are from each other, presumably that would actually be a given. I don't know the actual answer for this picture that's like off Google Images, and I think it's like a made up picture, but the distance between the positive and the negative, that would presumably be a given. That would be measured. What we want to calculate from the picture is the number of newtons per coulomb that we would experience at every point in space at a certain distance from those positive and negative. Like the positive and negative, the distance between the two, that's what's creating this whole situation. So we would know that going in, but what the picture is supposed to show is what the positive and negative are doing to every point in space. So what would be calculated from it, what we would calculate from the picture is the number of newtons per coulomb that we would experience at every point in space based on this picture. And yes, that absolutely could be calculated from the picture as long as we knew the scaling factor. That's why we pick a scaling factor at the beginning and then draw everything consistent with that, because absolutely, once we know the scaling factor, we totally can do calculations from the picture, and that's the point of it. So the picture is intense. I totally agree with you, direct chat person. The picture's intense, and listen, that's just the picture from just a proton and an electron. That's just a picture from a dipole. That's a picture from a hydrogen atom. Okay, I mean, this is a funny thing about physics. Like this is just hydrogen. Can you imagine? I don't know if you had Dr. Pro or, I mean, can you imagine my colleagues, the chemists in this department, like Dr. Prony, who deals with, like she deals with, I can barely understand hydrogen. She deals with molecules made of atoms with tons and tons of protons and electrons. Right. Awesome direct chat person who's saying, I can imagine that other intermolecular forces are insane. Right. In fact, the reason I'm dwelling, that you're absolutely right. I mean, that's awesome that you have that perspective. The reason that I'm spending so much time, and I know that I am, on like the intricacies of drawing these pictures or reading these pictures, even for these seemingly simple situations, is we need this kind of picture This is the simplest possible representation we can make for situations. And the situations, of course, get much more complex. So we need a method that's as simple as possible to handle. Like, look, I'm going to scroll. What we're going to look at eventually, like, and I don't mean eventually like weeks from now. We don't have weeks from now. I mean like minutes from now. We're going to start looking at pictures down here. These pictures are a little bit more intense, right? And these pictures, they're not even that, like the picture all the way to the right, C, is even more complicated than the pictures we just looked at. But all that is 3 protons and an electron. That's it. I mean, it's like beryllium, lithium, like after it lost 2 of its electrons because it got ionized. I mean, it's ionized lithium. Like for a chemist, that's super simple, right? But yeah, that's already a fairly intricate diagram. Now, and it gets much more complicated. But this is the way that we understand the way fields work in the world. We put these diagrams together as building blocks for more and more complicated situations. My goal here, and I'm not claiming, but yeah, really good observation. I'll leave it at that. Let me say one more thing about that. Because yes, I am not trying to make any of us experts in drawing these perfectly or anything. I'm not an expert. But what I'm trying to convince you, by the time I give you all these rules, and we're like halfway through the rules, what I want you to see by the end of these rules for drawing field line diagrams is that these field line pictures, which are calculational tools, they literally are calculators unto themselves, like the person just asked. Like, yes, once you draw these to scale, or you have a computer render them to scale, then they're absolutely used to compute things. The idea behind these pictures is it's not the following. It's not that, no, let me back up for a second again. Let me remind you, the picture represents force per charge. The picture represents magnitude and direction of force per charge at every location in space due to some source charge, some arrangement of source charge. The more complicated the arrangement of source charge, the more complicated the field line picture. The field line picture is meant to show how hard and in what direction we would be pushed at any and every given location in space that we could imagine. Okay, so it's meant to show magnitude and direction. Now, here's the thing. Well, I made the mistake. I misunderstood when I was in college. I thought the idea was if you could figure out how the magnitudes and directions worked at every point in space, then you could draw one of these pictures. I mean, I found the pictures totally intimidating, and I still sort of do, but I totally found them intimidating in college. And I assumed that it wasn't even, I assumed like, all right, if I'm lucky, I'll be able to read these someday, but I can't even imagine they would ever ask me to draw one or something. I assumed that in order to draw these pictures, you needed to know what the magnitude and the direction was doing at every point in space. That was a total misunderstanding on my part. And no wonder I was intimidated by the pictures. It's not that you need to know magnitude and direction in order to draw the pictures. It's the reverse. It's that if you follow the rules for drawing these pictures, the rules take care of themselves. The pictures draw themselves. I mean, they don't literally draw this, but if you just blindly follow the rules that I'm giving you now, then you end up creating a picture according to the rules. And then the picture shows you the magnitude and the direction of force waiting to happen at every location. That's why they're such a powerful tool. So put another way, even if you never draw one of these pictures in your life, some of you are somewhat experienced with computers, and some of you, write in code or do things in JavaScript or Python or blah, 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 whatever. Like, you can at least imagine that if I'm giving you these rules and you encoded these rules into a computer, into code, then someone comes along and gives you a situation, you apply your computer program, and then your computer program spits out a picture according to those rules. And now you see what the magnitude and the direction is doing at every point in space. We're not assuming that we can already hold that information in our brain. We're using these pictures to find out what is happening everywhere in space. So the rules are really important because they give us the script for seeing how information is distributed in space. Okay, the pictures can get even more complicated. I'll get back to these complicated pictures soon. Let me get back to the rules, though. But that's a great observation that someone just made. Wait, is there more in the chat? Oh, it was in, right. It was in rule 4. Yeah, I totally, and I realize now when I asked you all the question about the density, and then like I was all impressed that some people, yes, I had just told you the answer 5 minutes before that, but all right, we're finding out who's paying attention. But yes, and biochemistry. Yes, but oh yeah, dude, sorry. Right. So someone just put in the chat. Well, I guess that was to everybody. Hold on, let me just switch. I'm getting all my screens are getting me confused. Hang on 1 second. Hang on. Let me just say for a second, someone just, as you know, Marina just put in the everyone chat that biochemistry is also about protons and electrons. Oh yeah, totally true, Marina. And like, let me be clear, everything is all about this. Ultimately, like, let's get it straight. I mean, and I'm saying this with complete respect to all the sciences, but biology is built on chemistry. Chemistry is built on physics. Physics, you might argue, is built on math, I suppose, and math is built on theology. But what I mean is just that we're giving you the fundamental principles and the fundamental interactions that happen between the fundamental particles, and that's why that they're heady enough that we're sticking to the simple cases of like one particle and another particle. As you can see, just looking at what one proton does to one electron opens up a lot of concepts and a lot of details. But then everything you do in chemistry is all, when you move from physics to chemistry, you're zooming out, right? Things get less and less simple and more complex. That doesn't mean they get easier or harder. That depends on how you think about stuff. But when you go from physics to chemistry and then to biochemistry or bio, you're just zooming out more and more. It's all tethered to the same set of principles. And which one you like doing, physics or bio or chemistry, just has to do with where you like to set your zoom, right? I mean, but yes, of course, everything that's happening in the human body is ultimately governed by these proton-electron interactions. It's just that by the time you're zooming out and looking at life forms, you cannot bother with counting one proton at a time. Like, that's not your interest anymore. But absolutely, you're right that what you're getting in this class is the building block principles, and then when you get in the other classes, the applications of those principles. But it's all of a piece, absolutely. I can't say it any better than you already did. So why did I try? I don't know. So let me go back to the videotape. Let me go back to. Oh no, that's not what I meant to do. Wait. Let me go back to the next rule. Okay, so next rule. All right, so we did direction and magnitude. So now we go to the next rule. So now we're almost somewhere. Now we go to rule 5. Okay. Rule 5 says field lines can and do bend, as you're seeing in those pictures. They absolutely can curve. They do curve. But they always curve continuously, smoothly. Like they curve, but they don't turn corners. And again, and they certainly don't just stop. So they don't do anything discontinuous. Field lines, you can curve a field line, and sometimes you have to in order to follow rule 1 or 2 or 3. You can, when you're drawing a field line, you can make one curve, but the curve has to be as gradual and as smooth as you could possibly make it. And then if the field line next to it also has to curve, it's going to curve in a way that's very similar to the first one. Everything happens gradually and smoothly when you're drawing the field lines. But absolutely, they can curve and bend. Again, they are not vectors. They are a different representation. As much as they can curve and bend, however, they cannot cross. It says field lines never cross. Now, why is that? Because each field line is a representation of field, and field, by definition, by the equation, field is defined to be net electrostatic force per charge. A field line is a indication of the combined impacts of all of the sources acting together. So the picture that we keep looking at, which I'll go back to in a moment, but the picture of the lines up here in space is what would happen in space due to the presence of a proton over here and an electron over here, right? Where we're saying to ourselves is, okay, the proton over here pushed up and to the right. It planted an upright vector sitting right there. And then the electron over here is pulling down and to the right. So it planted its own little vector pointing down and to the right. So there's a vector from one and there's a vector from the other. The field line is what we get after we've added those two vectors together and come up with one result, saying what the net effect is due to both of these charges. So if you ever looked at some, oh yes, thank you, right. And I'm actually almost, yes, we are now at 6 o'clock. Totally appreciate that. I really do. And I'm not going to end right on this dot, but I'm going to start wrapping soon. We're actually doing better than yes, thank you. Okay. So if you ever saw a picture of supposedly a field lines and you saw two field lines crossing, and you're like, wait, what is these two field lines? And the person was like, well, right, because there's one line like coming from this positive over here, but there's this other line coming from that negative over there, or whatever, going to that negative over there. But what that means is they haven't finished making their picture. It means you're looking at a rough draft. Like, yes, in our minds, as we're constructing these lines, we take the contribution from this source and the contribution from that source. But ultimately, the lines are supposed to be the net effect of everything producing them. So when you're all said and done, lines can't cross. The lines already take into account the crossings. I don't know if that makes sense or not, but that's the deal. So let's move on. Thanks to the time check. Let's go to the next. So, but if you notice in those pictures, you see a lot of bending lines. You don't see any crossing lines. Not a coincidence. Now rule 6, I'm going to put in parentheses, actually. I mean, I'm going to tell it to you, but rule 6 is true. I mean, it is a true, but it's almost more like an observation. Like, the truth is, you don't have to try and find. It's more like a checkpoint. Because if you follow the other rules correctly, if you follow the first 5 rules, this rule will take care of itself automatically. It'll just happen automatically. But what it says is a field line diagram should grow increasingly simple or symmetric or uniform as we look farther and farther from the source charge. All right. As you look farther and farther toward the edges of a page, if you look farther and farther away from the source charges, the lines should start looking more and more like parallel lines, really, or certainly, yeah. Because as you get farther and farther away from source distribution, you should see a simpler and simpler field situation. Because remember, fundamentally, all of this is about E equals K Q over R squared. It's all about the fields are directly proportional. The strength of a field is directly proportional to the strength of charge, and it's inversely proportional to the square of the distance from the charge. So as you get farther and farther from any one point source, the field grows weaker and weaker. It starts approaching 0 as you approach infinite separation from the charge. But so if you have a really complicated field line diagram, it's because you have a really complicated distribution of charge. If the field lines are doing really funny things, it's because you have maybe 3 positives over here, but then you have like 7 negatives over here or something like that. So this is creating lines that are doing one thing, and these are creating lines that are doing another thing. So the interplay of the lines is all complicated and intricate in between the two charges. But as you get farther and farther away, like this charge is doing less and less and less, period. The impact on space is vanishing. And the impact on space from this charge is getting less and less and less. So any distinction between the two impacts or any conflict between the two impacts is getting less and less and less. It's growing less and less important that this is a different bunch of charges from this bunch of charges, because as you get farther and farther away, each one of them is not doing that much at all. So it should be the case that as complicated and intricate as these field lines looked, they really should look the most complicated in the middle, close to the source charges, and they should be getting less and less complicated as you spread out. I'm going to go back to the pictures one last time in a moment, but let me give you the last most important rule, and then we're going to look at it in regard to all these things, and that'll be done for there. I mean, then we'll change the subject completely, and I'll let you talk more, or I'll encourage you to talk more. The last rule is this, rule 7, is a field line diagram should be the simplest, smoothest, most symmetric picture you could possibly draw once you've applied rules 1 through 6, or really rules 1 through 5, because again, 6 will take care of itself automatically. So these pictures look really crazy intricate, but actually they are the result of a fairly straightforward algorithm that any one of us could follow. Like, we could all draw these pictures. Our pictures wouldn't be as neat, and or at least mine wouldn't be as neat and precise as these computer rendered ones, but they would be better than we would think. I'm going to go back to the picture now and show you what I mean, and then we will stop. Like, let's look at the most complicated. Just seem to get any more complicated. Hold on. Yeah, all right. Let's look at the most complicated. And yeah. Yeah, all right. Let's look at the most complicated option here, option C, right? It is pretty darn intricate. I mean, it's pretty darn intricate. I mean, and what this picture is, what picture C is, as it says above it, is a +3 nearby a -1. Now, they're together the source. Again, this picture is not showing you what one thing is doing to the other. It's showing you the combined effect of both on space. Now, if I just walked up to you, or if you just walked up to me and said, give me the field line picture of a 3 protons nearby 1 electron, of course I would find that intimidating at first. I would say, dude, I don't freaking know how to draw that. But I actually would, and you actually would. This is what you do. Like, to what that picture is, picture C is someone first came up with a scaling factor. Their scaling factor was something like, let's say 16 lines. I'm making this up, but something like 16 lines per 1 coulomb of charge. And then they said to themselves, okay, I've got a 3 coulomb charge over here, and I've got a 1 coulomb charge over here. So and I know the rule that says all lines have to like start from positives, and they have to end at negatives if they start or end at all. So what the person did making this picture is they realized, okay, supposedly my positive charge is 3 times as strong as my negative. So they start with the negatives. If I were drawing this picture, I would start with that negative and say, okay, I've got to have 16 lines. I'm just making up. I've got to have 16 lines coming into that negative. I will start in my mind by making 16 lines arranged symmetrically coming into that one negative point, as though the point were just by itself in space. I'm going to sketch lightly with a pencil 16 lines coming in to that negative. Then I'm going to go over to my positive and say, okay, the positive is supposedly 3 times as strong. So I'm going to make 48 lines come out of that positive, right? I mean, it's hard. I mean, or we could have come up with a different scaling factor, whatever. But whatever, if 16 is the scaling factor, then now 3 times that, 48 have to come out of the positive. Now, here's why I started with the negative, though, because not coincidentally, of the 48 that come out of the positive, 16 of them will be the ones that are going into the negative. Like, first and foremost, I'm going to match up any lines that I can. So I'm going to have 16 lines that go from positive to the negative, which means you know, if you heard how I keep saying you draw the lines as symmetrically as you can, as symmetrically as you can. Well, yes, as you can, given the situation. So if I just had one point, I'd have 16 lines coming out of it equally in all directions. But I don't just have one point, I have two. They're supposed to be connected. So that's why, if you look at this picture, you start seeing like all the negatives that could just come slamming into the light blue dot do. But if you go to the right-hand side of the negative blue dot, you notice every line that came out of, every line that's going in to the negative light blue dot, every line that's coming in is necessarily coming from the positive, because there are enough positives to do that. So the lines on the right side of the negative blue dot started bending over to be connected up with the positive. So they're not perfectly symmetric. They're as symmetric as they can be, but as symmetric as they can be by following all the other rules. On the right side of the negative, I have lines that are bending to match up to join in with the positive. But notice, so they're bending. So I'm following rule number 4 or whatever it is, but they're bending as smoothly as possible. Nothing is bending as a surprise. There's no one line that just bends wildly in a way that's different from any other line. Everything is gradual and smooth. So if I just start with the idea that every single line that went into the negative had to come out of the positive, and the positive and negative are where they are, then it forces me to just start smoothly bending those lines over and hitting onto the positive. Of the 32 leftover lines of positive that have no negative to hit, right? Because again, the positive is 3 times as strong. That means I'll have 32 lines that should still be symmetrically arranged, like not random, but the 32 lines that didn't have a partner over in the negative, they just go off to infinity as smoothly as possible. And if I were really careful following those rules, it turns out there would be no other way to make this picture but the way that I see it in C. I mean, if the positive became 4 times as strong, the picture would be even different. But ultimately, if you just follow those rules, there turns out to be one and only one way to, as simply and symmetrically and smoothly and gradually as possible, follow the basic rules of lines have to go from positive to negative, lines can bend, but they cannot cross, and there has to be a consistent number of lines for every unit of source charge. That's it. That's what the pictures are doing. I'm going to pause for a second. First of all, there's something in the chat, or maybe I already, let me see. Oh, cool. Oh, that's very interesting. Someone's saying in the chat that C is starting to look like the sun and the earth. That's a cool observation. And starting to, because, right, in this case, we have a charge that's 3 times as big as the other charge, and whereas the sun is like even bigger than that, it's more extreme. So that's a really good, so yes, if you took this to its extreme, it would really start looking like the sun and the earth. But there's one more, that's a really cool observation, but there is one qualification that I have to throw in too. Remember, this is, you're right, the sun is like a lot bigger than the earth, and this is like a set of protons that's a lot bigger than the set of electrons. But the only thing is, remember, this is protons and electrons, so these have pushes and pulls. With the sun and the earth, it's all pull. So the diagram would actually look, to be honest, with the sun, with the sun and the earth, it would look weirdly, it would look a little bit more like what diagram B looks like, only with all the arrows going in rather than out. But that may be a weird thing for me to say. You may want to think about that, but it seems like C is more appropriately like gravity, because it seems like what you're looking at is attraction there. But remember, these field lines are not meant to show, and it's true, the sun, of course, does attract the earth and vice versa. But remember, these diagrams are not trying to show what's happening in between the proton and electron or the sun and the earth. It's actually meant to show the combined effect of, say, the sun and the earth on the rest of the space. So oddly, so it's a really good observation, but I don't know if you understand what I'm qualifying, but I'm gonna shift gears, and I just want to oh wait, oh, here. Just to respond back to how complicated these things can get. Like I'm just scrolling, just again, like if you look at the black, I'm just scrolling. Can you see? Yeah. I mean, like these are all different field line diagrams, just of random situations. The more complicated the situation, I mean, the more complicated the field line picture, the more complicated the distribution of charge. The main thing to take away from all these pictures, though, no matter where I'm scrolling, no matter what pictures I'm looking at, you notice that every one of these pictures, no matter how intricate it is, it's always an interplay of symmetry and asymmetry. There's always some kind of basic evident symmetry going on, and then there's some kind of asymmetry. In fact, I want, actually, here's our takeaway. We're going to write one thing down, and we're going to shift the topic entirely, and you'll be talking, hopefully. But yeah, like, look how, I mean, they can get, but they're always, and they're kind of beautiful in their own way, I think. But no matter how intricate they get, there's always like some symmetry and some asymmetry. Or put another way, what distinguishes one picture from another is the type of asymmetry it has. But it's always patterns, like, oh yeah, that one. So I'm going to, oh, sorry. Okay. The takeaway of this is, and remember, and you may want to write this down too. Remember, a field is a mechanism by which a point in space over here knows what's going on over here. Field is the mechanism or the medium by virtue of which a point in space over here accesses the information describing what's happening at a point in space over here. That's what the field is. Field lines capture the field, indicate, represent, capture the field in the following way. Field lines are only as asymmetric as the distribution of source charge that created them. Like if there was, remember, if there's just one point of charge creating field, the field lines are as symmetric as they could possibly be. They all, if there's one point of charge over here, it radiates out field lines in all directions. So any point in space over here is like, oh, there's a field line. Or any point in space over here is like, hey, the field lines are not very crowded over here. So the field's kind of weak over here. But I see that the field lines are coming from over there. So I guess there's a charge over there pretty far away, right? Like that's the idea. Like, and it's numerical, like someone was asking in the direct chat. Like the real idea is if you're a point in space over here, and there's a certain number of field lines over here, if you know the scaling factor and all that, then you know exactly how strong the field is over here, which means you know, or how weak. So you know how big there is a charge somewhere in space, and you trace the field line back in principle, and you're like, oh, the field lines are coming from over there. So I guess there's a charge this far away of this magnitude, right? That's what the field lines are showing. And the more symmetric the field lines are, the more symmetric the original thing that created them is. If there's just one point, it creates perfectly symmetrical lines. The more complicated the lines, that indicates how complicated the source is. So the asymmetry of the lines indicates the asymmetry of the source. That's the way the information is being conveyed, the information of what's over here to what's going on over there. And you know, one definition you may have heard, one sort of popular colloquial definition for information is the difference that makes a difference. That's literally what we're saying here with field lines. The more different, the more asymmetric, the more unpatterned they are, the more they're telling us the specificity of what's happening over here with regard to charge. Okay, so that's the deal with electrostatic fields, electrostatic field lines. Field lines are the difference that make a difference. They indicate, field lines indicate over at this point in space the information of what's going on over here at this point in space. That's fields. Now I'm going to, in fact, you know what? Let's all take, this is perfect. We've got, if we take a 5-minute break, it'll be 6:30. We'll have 40 minutes for us to be a little bit more relaxed and talk about your last lab. So let's take a 5-minute break if that's cool. I can't even see you right now, but I assume that's cool. Can I get a thumbs up? It's a 5-minute break. So Eugen, is that cool? That's okay. Thank you. Okay. 5-minute break. I'm going to Okay. So I'm back. I'm gonna ask you, let's see, you're all okay. We should start up again. I'm gonna wow, fat. Thank you. That was awesome, Marina. Thank you, Marina. And Jake, thank you both. Okay, awesome. Keep them up. Let's okay. Or yes, keep and if you can keep wait, where did Marina just go? Oh, thank you. Oh, and there's I love this class. Okay, thank you, SpongeBob. I mean Ariana. Thank you, Marina. I think that's right. That's like a hippified. That's like what SpongeBob looked like when he was me. Okay, thank you, Ashton. Thank you, Marina. Awesome. Wait, but oh, Patrick. Oh, yes. I'm sorry. Right. Yes, I get it. But yes. Okay. Yes. How can I? Right. Okay. Well, okay. So we're gonna start again. This is right. This is Patrick. Oh my God. Okay. Patrick is so. I mean, SpongeBob is so like. I don't know what. Okay. Okay. So this is my informal way of saying let's regather. Let's start again. But side a soul-driven character. Wow, Ariana, you are today is definitely your yes. By the way, side note, I'm just saying, okay, I haven't seen a movie and had not seen a movie in the theater in so long. I didn't even know that theaters now, like, and maybe they're not all like this, but this whole business that you have like that you sit back in like a reclining chair and have a huge like tray with they've seemed much more luxurious now than I ever remember them. But I hadn't seen a movie in so long, and I just want to say, what brought me back to the theater? You might ask, like, what did I actually get off my sorry butt to actually see? Oh, you could guess, I'm sure, if you've been paying attention to any of this all semester. Absolutely, the one movie choice that inspired me to go to the theater, and I'm doing a big unpaid advertising plug for right. Yeah, your guess. Wait, let me just see. I'm sure you could guess. Well, can we? Well, anyway, what I saw that I'm highly recommending to anybody who, why am I saying this? I don't know, just to bring us back, is the Mario movie. Oh God, does it rock as far as I'm concerned. It's so what crushes, whatever. It so does what it should do and what I wanted it to do. Yeah, no, totally. I thought you knew it. Yeah. But yes, I mean, and it's oh, I haven't seen the Sonic yet. Yeah, I kind of want to see that too. Good point. I forgot. But I mean, and like if you haven't seen Jack Black do Bowser, you haven't lived. That's all I'm saying. I mean, if you're interested in those things at all, which there's also no reason to be if you don't want to be. But okay, that's it. Yeah. Yeah. Oh my God, the Peaches thing. Right, exactly. I was hoping I could get a little friendliness on that. Yes. I mean, that is like the best thing that has happened in 5 years of culture. Yeah, totally. He should get right. Okay. He should get an Oscar for that. Oh my God, the Peaches. And it is so great too, because I even knew it was Jack Black. I even went there to see Jack Black. But then once it happened, like one tribute to the movie, in my opinion, I can't believe I'm talking about this, but yes, I do believe it. Is like once he started doing that thing, and I hadn't seen the video before. I hadn't, but when he started, playing Peaches on the piano and everything in the movie, I was so transported. I literally did not even remember that it was Jack Black, even though that's what I went to see practically. Like, it's just so, I was just transported. I don't know. And the platform, like, okay, whatever. All right, so let's get back to physics. Here's my question to you. But yeah, you know why I'm talking about that? Because it's just pure joy. Because life should have some space for just pure joy with no cost. And the only cost to any of that, it was the cost of the movie. Okay, anyway, physics. I want you guys to talk to me. My impression is that the last lab you did, I believe, you did the interference simulation lab. I know it was a simulation. That's a bummer. Okay, but you did, I believe, you did the wave interference ripple tank simulation thing. And I believe you had two motions. one of which was delta L equals n lambda over 2, like true or false, and the other of which is true or false, light travels as a collection of oscillators staggered in phase by a constant amount. Something to that effect. Am I even on page at all? Is that roughly what your lab did? I mean, not exactly, but is that, oh, yeah. Oh, by the way, no, fair enough. Sorry, I missed the chat. Yeah, there is great physics in Mario Brothers. Totally agreed. I don't mean to go back to that, but I'm just seeing the chat. Oh, yeah. And good video games are like super physics driven. Absolutely. But okay. So, but yes, Ashton, you're saying yep to what I just asked about the lab. Is that like you're actually keeping the class going, unlike me? Is that's a okay? Yes, sir. Yes, sir. Oh my God, I don't know about the sir, but okay. Cool. Well, that said, let me start by asking you guys, what did you conclude about those two motions? Like one true, one false, two true. Like, okay, Ashton, go for it. And please feel free to talk. I mean, I've talked way too much for my sake or your sake. So just like take over. I mean, if you can. Talk to me, Ashton. What do you go for it?
All right. So my group believed that both claims were true. And for the first claim, our explanation was that the length of a string is equal to n, in like quotes, n halves of a wavelength. And then for claim 2, we said that light is a set of infinite harmonic oscillators. And those were the things that we had to back it up.
Whoa, very cool. Okay, awesome. Totally on point. Thank you. The reason I just made a weird face, I'm just intrigued by, and I'm totally with you. I'm totally with you. I'm intrigued by one word that you just threw in. I'm not saying it's wrong. It may really be right. I'm just not sure if it came from me or Mercedes or you. And this is an honest thing. I'm just curious. You mentioned the word infinite. You said a collection, or you said an infinite collection of oscillators. I'm on it, and you may not even remember, by the way, but I'm honestly asking, is that your word, or was that like written as part of the motion by Mercedes, or did that, like, where did that word come from?
I guess that was my word.
Okay.
I don't remember, but I think if she said that, I would have remembered her saying it. So
okay. Fair enough. And I'm not saying it's wrong. I'm just intrigued because it's a powerful word. Okay, cool. Okay, so that's one person. So Ashton is saying her group said that the mathematical motion was true and that the verbal motion was true. Cool. And I'm saying cool because I'm totally with it. I'm not literally necessarily committing that I agree yet. But I'm curious, anybody else want to add? Did anybody else get the same thing as what Ashton just said? I mean, did any other group also come to that conclusion? Eugene is giving me a side eye. Wait, or maybe she was in the same. Did anybody get a different? Oh, that's Jake. Okay, I mean, Jake is saying yes. And I'm assuming that Jake is in a different group, but Jake's group is saying they also got, okay, fine. Now let me ask, did any group get anything different?
I'm in the same group as Ashton, actually.
Oh, okay. Sorry. Okay. So you agree with, do you?
Yes.
Okay.
Yes.
All right, cool. All right. I really should, yeah, okay. Okay. Then I'm going to push this. All right. Am I prepared to commit? Well, I am married. Am I prepared to commit that those two answers are true? I think since it's 6:40, yes, I am. And maybe Mercedes already did. I don't know, but I agree. That's awesome. I think we're making progress. I agree that both those statements are true. That's cool. Now let's go a little further. Why? I'm willing, in fact, and I'd like to ask someone, I've heard now from Ashton, and I've heard from Jake, and I've heard from Eugen in principle. Is there anybody else in the room that could begin to fill in why? And when I say why, I mean, that's pretty open-ended, but I mean, either why do you agree with the math statement? Like what, like you could just tell me anything. You could just begin. If someone wants to just even screen share something, or you could just even begin, or you could even begin to like tell me what that math thing even means. You could go like that. That would be, in fact, pretty helpful. Or if anybody in the room is sort of intimidated by the math or not even sure that they know what was going on with math, but feels that they have some clue as to why they agreed with the English, I could hear that too. I don't even know at this moment whether you're thinking that the English is linked to the math or not. We'll find, but I'd love to hear anybody's reasoning on any level of like how you came to the conclusion of yes with either of those two statements. And I would preferably for the moment, like someone, if possible, that isn't Ashton or Eugene or Jake, just for the moment, just to keep this scramble up. Can anybody give me any cut? And again, even if you think the question why is too big, if you just want, if anybody just wants to share anything, like what any of the terms in the math equation means, or any data that they got, like just like get this party started of like, what the heck were we trying to actually analyze on Monday? Bueller, anyone? You know how hard it is to be me, guys? No, seriously, wait, anyway. Or, okay, I'm gonna do the thing again. Can you just raise your hand if you're with me, right? Like if you hear me right now, I mean, your electronic hand. That was okay, cool. Okay, okay. So can I ask, cool. So can I ask, and I will bring it back to those guys. It's not that I don't want to hear from them. It's just, I want to hear from as many people as possible. Oh my God, Siri is recording this lecture. What the, sorry, oh my God, or Mrs. Google, one of them. Is it possible just because like, is it possible that Sylvie or Ashley or Kayla, just because you just raised your hand, I'm not putting you on the spot. But since you did just raise your hand, since you are hearing me, is there any, do you want to throw it? Like, do you want to just even, like, could you, for example, maybe one of you even, if you could even tell me if you were more comfortable with the math part or the English part, I would even definitely take that as constructive input. Like Kayla or Sylvie or anyone, obviously, but going once. Oh, interesting. Okay, and by the way, thank you, Sylvie, for stepping up. It's particularly hard to step up when I'm putting this kind of pressure. Okay, the math part is good. Oh, okay, wait. Okay, Sylvie liked the math part. Kayla understood the wording. Cool. Fair enough. That's honest math. I had to ask my lab mates. Fair. And that was the thing. Oh, and cool. Good. By the way, thank you for keeping this ice broken, all of you, because I'm now noticing things are starting to happen in the direct chat, which is great because I can work with that. And I encourage again, and if you don't want to like be sharing in front of the other, if it's like too whatever, please put, even if you want to just put something in the direct chat where you got lost, where you didn't understand, I can work with that. And one person already is, so that's great. Hold on. Oh, very interesting. Whoa. Okay. There's something in the direct chat that might really get this. I want to think what I say about it. Okay. There's something in the chat. Okay, I'm going to read. I love what's in the chat. I'm not saying it's 100% correct. I mean, it's very nuanced what's in the chat. I'm going to read it out loud just for consideration. And then I think I know what I want to ask everybody. Oh wait, no. You're not thinking too hard on. Okay, so the person in the direct chat. No. We are now at the point of the course where it is definitely time to think. We are getting to that point where we are here to put these pieces together now, and we are here to like step back and try to see what's going on, i.e. think. So for example, one person in the direct chat put, for the written statement, I read that light is composed of charges that can transfer back and forth in order to continue simple motion and displacement. All right, and it might also mean in order to constitute simple motion and displacement. But let me read that again. And I'm not saying it's 100. I'm saying we're definitely getting somewhere with this. I wouldn't fully take it to the bank, but I read that light is composed of charges that can transfer back and forth in order to continue simple motion maybe simple harmonic motion and displacement. Now, that's very much like on the topic of what we're trying to deal with here. I'm going to back all the way up and ask all of you. I'm going to ask a question based on this and based on what like 3 people already raised their hand and stuff. The complicated sentence the motion that I sort of volunteered and then Ashton sort of read out loud, and now here's another version from the direct chat. It's a lot of words, right? I mean, it may be easier for some of us than dealing with the math, but for some of us, it may be so many words that we freaking just would like a simple equation. What I want to back up and ask all of you to put in the direct chat, those huge set of complicated words from the English true false thing, if you had to translate that into 4 words or fewer, like 4 words, what is, and I have a sentence in mind. That sentence of English that I asked you to say if it's true or false is a very complicated sentence, and it's complicated for a reason. Ultimately, I do think it's as simple as it can be ultimately, but you could, to get this conversation rolling, or continue it rolling, you could simplify that statement vastly and reduce it to a sentence of basically 4 words or 5 words if you want. Like, I would like to know from all of you, for as many as possible, in as simple terms as you can you translate, all of you, whether you thought it was true or false or whatever, can you take that super complicated sentence that I gave you, and can all of you please try your best in the direct chat to reduce it to translate it to as simple a sentence as you can? Like, what's the basic thing that I'm trying to ask you, or what's the basic thing in English that your last lab was trying to establish? Okay, there's things happening in the chat. Wait, there's one person in the chat who is doing exactly what I'm saying. Yes, there's one person in the chat. Wait. Oh no! Oh, you're raising your hand. Oh, cool. Wait, are you sorry? Right now, I want it private. I totally see you, Eugene. That's awesome. For the moment, I will call on you, but for the moment, could you put it in the private chat? There's one thing I think in the private chat, and I totally agree with what's in the private chat right now for what it's worth, but I want to see a lot. So Eugene, yeah, I want from all of you. Like, and this is I know we're almost at the end of the, okay, I can repeat. Yeah. Oh, sorry. Okay, now I get it. Okay, yes, I can repeat. I'm sorry. Okay. The original sentence that we're trying to translate right now, everybody, and I'm really going to ask, I want people that I don't hear from a lot to do this in the direct. The original sentence is that light can be considered a collection of harmonic oscillators staggered in phase by a constant amount. That was my version of the sentence. Again, Mercedes might have said it slightly differently. Ashton said it slightly differently. One person in the direct chat said it. But basically the sentence, I'll say it one more time. True or false, light can be considered a collection of harmonic oscillators staggered in phase by a constant amount. I'm a goldfish. Sorry. That's good. I'm good. Right. Okay. Wait, and I'm going to repeat it again. Okay, cool. Wait, I'm going to, now some people in the chat are saying like whether it's true or false. Yeah, I'm willing to agree it's true, but what I'm asking for but thank you for participating, definitely. What I'm asking now is for you to translate it for all of you. I want you to simplify it. Like, what the heck am I trying to say in simple words? If I say light is a collection of harmonic oscillators staggered in phase by a constant amount, what the heck in simple terms am I trying to say about light? Like, if it is true. So I'm going to look. So I see some things in the chat. I see I'm a goldfish, which is hilarious, but not, which is really hilarious. Is that not what, but I'm not sure. Wait, do you see my goldfish? Okay. I see like things like, I see one thing that's so correct that I'm not going to repeat it just yet because I want to hear, but I see things like light is constantly moving in time. I see things like light oscillates in a constant amount. I see, and then I see 2 things in here which are exactly what Then I see if there is there a huge difference in light and a light spectrum? That's interesting. I'm going to wait for one more thing in the chat. Again, I'm saying, what does it mean to say? If I say to you, if I say sound moves as a, or can be considered a collection of harmonic oscillators staggered in phase by a constant amount. If I say that about sound, what am I saying about sound? Oh, cool. All right, I just saw another thing in the direct chat, which is totally what I'm looking for. Okay, there's enough in the direct chat. No, and thank you. I'm not going to say anybody's names, but thank you. That was a lot of you. Okay. Yeah, those of you who said so, those of you who use the word wave, that's what I'm looking for here. And I'm not trying to trick anybody, but let's pause for a second. The whole first part of this course, the whole stuff that went up to the midterm exam, may it rest in peace, like the last question of the midterm exam was all about like everything. We did all of this stuff with harmonic oscillation at the beginning of the course. And then we moved from harmonic oscillation to like harmonic oscillators, like in phase or not in phase with each other. And then we built a bunch of harmonic oscillators, like all staggered in phase by a constant amount. And we put those all things together. And we ultimately had the idea of a wave pulse propagating through space. Like our whole idea, ultimately, when we finally built up an unthingy motion, when we finally were looking, and it took us a while, but when we were finally looking at things like water waves, or even better, like sound waves, what we were ultimately saying is that wave motion, waves, a wave is not a thing. That was our big point, really our big takeaway from the first bulk of the semester, that a wave is not a thing. A wave motion is a collection of many, many little things, all oscillating cosinusoidally in time, and then all arranged cosinusoidally in space. Like the reason we spent all that time studying oscillation was that so that we could put together in our minds and in the lab a bunch of oscillators together in a super intricate way and ultimately create the propagation of a wave pulse. And remember, the big thing about a wave pulse, specifically, for example, sound, the big thing about sound is, on the one hand, we're saying a sound wave is a real thing. It really is measurable, observable, predictable, trackable in space and time. A sound wave could not exist unless a bunch of matter existed in space and time. A bunch of little air molecules called the medium all oscillate in a very, very intricate way through space and time to create this sound wave. So a bunch of air particles oscillate harmonically, but staggered in phase by a constant amount. Like that's ultimately we were trying to say, and ultimately the conclusion of like question 4 on the midterm was that if you put a bunch of air molecules together and have them all oscillate harmonically in time and space, then you get this thing called a sound wave pulse. But here's my big reminder or big takeaway of all that is that once all of these air molecules are oscillating in a manner that is staggered in phase by a constant amount, then they create this thing called a wave pulse, which is itself not a thing. Remember again, in other words, for sound to leave my mouth and reach your ears, a bunch of air must be moving, but no individual bit of air ever travels from my mouth to your ears. When sound goes from my mouth to your ears, it requires a bunch of, and it relies on a bunch of air moving, but no air moves from my mouth to your ears. That's the nature of a wave motion. Wave motion is non-particular motion. So when we ask in the lab from last week when we say, hey, can light be considered a collection of harmonic oscillators staggered in phase by a constant amount? What we're really asking is, hey, can light be considered a wave? That's the question of the lab. When we say true or false, light moves as a wave. I mean, when we said that thing that we said, we're really asking, based on what we saw in the lab, can we infer that light travels as a wave? Now, I'm going to pause for a second. A lot of you did put that in the chat, which is awesome. Awesome. Some of you didn't, but I would guess. Some of you might be thinking, oh, that's what you were looking for, Yaverbaum? Like, oh, that's what you're talking about? Well, first of all, oh, yeah, I knew that. I just didn't think that's what you were talking about when you said all this nonsense about like phase staggered oscillators and yada, yada. Or you might be thinking, you might be thinking, oh, okay, well, if that's all we're talking about of whether light's a wave, and I did understand that, Yaverbaum, if that's all we're talking about, why are you making it so complicated with all this phase staggered oscillator crap? Like if any of you are thinking like, oh, well, light's a wave, that's what you're saying. Why don't you just freaking say it? Yeah, here's why. Because, well, wait, I'm going to pause for a second. Wait, right. Wait, sorry, I'm pausing for a second because I'm seeing the chat. Yes, wait. Okay, sorry. Space. Right. Okay. Sound always travels due to energy and vibrations. Good. Yes, wave. Awesome. In space, no one can hear you scream. No medium of oscillation to carry a sound wave. Right. Awesome. So, yes, you're with me. So, first of all, okay, again, what I'm saying is actually the math, all the stuff you were doing in the lab on Monday was geared toward trying to establish whether the whole point of the lab is to accumulate a bunch of evidence that at the end of the day, if done properly, strongly suggests that light travels as a wave. We may or may not have time to like work through that evidence today, but yes, that was the point. And by the way, again, I do understand that a lot of you probably understood that, whether or not you put it in the chat right now. If the math motion was true, which it was, if light actually does interfere through those slits, or put another way, really, if it is possible that light coming from over here can hit light from over here and make darkness, which really is what you were talking about in that simulation, like even before you get to the mathematical details, like what you're looking at an interference pattern. You're looking at that if light goes through two slits and lands on a screen on the other side. Wait, I'm sorry. Sorry, let me pause for a second. I'm sorry, I'm getting ahead of myself. The simulation you did, sorry, it wasn't actually about light, it was about water and ripple tank, right? Or tell me. I mean, either way, my ultimate point is the same, but I just got myself confused. The simulation that you did, were you actually, and I know it was a simulation, I know it was like on computer and it was fake, but was it investigating the way light moves through slits, or was it investigating the way water moves through slits?
Pretty sure it was water.
Okay. So let me back up for a second. Thank you. So the water, the water that was moving through the slits, if you think the whole idea is that water goes through here, water goes through here, water wave goes like a water crest goes through here, a water crest goes through there, but then across from the slits where you're looking, some places you're getting crests and some places you're getting troughs. Like with the water, it is possible for a bunch of water to come through here, a bunch of water to come through here, and over on the other side, see a very small amount of water, because a crest can hit a trough and cancel each other out. Like waves can do that. Waves can interfere constructively or destructively. The crest of one wave can meet the trough of another wave and make no wave. Baseballs, basketballs, electrons, planets, they can't do that. You can't have a planet hit another planet and combine into each other and make no planet, right? So you're looking at a phenomenon that is 100% about waves. The reason I made the sentence so complicated, so sorry, so you were looking at something waves do. Waves interfere. Waves make interference patterns. Only waves make interference patterns. Only two waves can be in the same place at the same time and interfere with each other and make a new situation. Two particles, by definition, going back to the first day of this class, two particles cannot be in the same place at the same time and create anything. One particle will knock another particle out of the way. Waves apparently can combine and make new things or make each other disappear. You were looking at what waves were doing. The question is, after seeing what waves of water can do in a simulation, the question is, have we ever seen light do that? Have we ever seen light go through two slits and create darkness? If so, if we've ever in our life seen light pass through two slits and make darkness, then that might suggest that light travels as a wave, which is our ultimate question here. Why I made the sentence so complicated sounding, I'm not trying to trick anybody, but why I made the sentence so complicated sounding is twofold. One, because I want to tie together the semester. I want to constantly reinforce to you what a wave really is. According to the first half of the semester, a wave is a collection of harmonic oscillators. But two, because it's very easy to say, and many people have said, it's very easy to say, I think light acts like a wave for a variety of reasons, such as I feel like I've seen light plus light make darkness. I feel like I've seen, for example, if you've ever seen a cracked windshield and you see lots of band of light and darkness in the cracked windshield, or if in another class you've ever looked through if you've ever looked through I can't believe I just forgot spectroscopes and seen light make a pattern of light and dark, or different color, you might easily or put another way, if you've ever worked in the theater and you shine a red spotlight down on the stage and you shine a blue light down on the stage, and they both, and the blue light doesn't knock the red light out of the way, right? You might say, oh, and they combine together and they make purple or something like that. You might say, I think there's a lot of evidence to suggest that light is not a thing. Light behaves like a wave. And I'm not saying that's wrong. But the reason I made the sentence so complicated is I want to remind you that if we believe that light is a wave, and we'll of course continue this discussion in one of our last classes next week, and we'll wrap up this whole thing next week. If we believe light is a wave, we have to remember the whole first semester, part of the semester, and realize that to believe that light is a wave is to believe that light is a wiggle. It's to believe that light itself is not a thing, right? That actually, right, to believe that light is a wave is to believe that there are a bunch of things that are all vibrating back and forth to create this phenomenon called light. Like when people just say light is a wave, it seems like a very casual, easy thing to commit to, unless we remember that to say light, remember what it means to say that sound is a wave. To say that sound is a wave is to say that there's no such thing as a bit of sound. To say that sound is a wave is to say that a bunch of things called air all constitute a big medium, and the bunch of little particles called air vibrate back and forth in a very intricate pattern in order to make the sound travel. To say, and we're just about done, I know, but to say that sound is a wave is to say that sound is not a thing. There is no thing of sound. There is no such thing as a particle of sound. There are particles of other things that when they gather and behave in a very, very intricate way, they create a phenomenon known as sound. And like someone put in the chat, it's for that reason we believe that so strongly about sound that when you go into outer space and there is no air molecules in outer space, there's nothing to oscillate harmonically in time and space, then there is nothing to carry the sound and there is no sound in outer space. Sound is not air, but you can't have sound without air or water or something like that wiggling. So sound is not a thing. It's a wiggle that requires a medium of wigglers to transmit it through. Now the lab, and I know we've got like 4 minutes and then I'll wrap up. The lab was meant to show you something, to show you another property of waves that we had never really studied before, the property known as interference and interference patterns. The lab is meant to remind you that things that interfere, where situations where crests can meet troughs and create nothingness, and situations where two entities can be at the same place at the same time, that usually indicates wave motion. So the lab is meant to like jog our brains and say, if anybody could ever do this with light, if anybody could ever shine light through two slits and have it create an interference of dark and light patterns, then we could infer that light is a wave. And the truth is, since we have 2 minutes and we only have one more class left, let me tell you that in 1809, a man named Thomas Young absolutely did do that. Or 1806, Thomas Young absolutely did set, for the first time, and we've done it a million times since, he did send light through really thin slits and create a pattern on a screen where we saw light, dark, light, dark, light, dark. So Thomas Young said, okay, I guess light is not a thing. It's a collection of harmonic oscillators staggered in phase by a constant amount. But the thing with 3 minutes left, so that's like, so far, that's, I'm telling you that. I'm telling you, I agree with you. If you think that you've ever pictured or could picture or observed, or that anybody in history has ever observed light to do the kind of stuff that your simulated water waves did, you're correct. And if you think that means that we can call light a wave, or that light motion, that the motion of light from here to there is the motion of some kind of wave from here to there, then you are correct. But the reason I made the sentence as elaborate as I did is I want to remind you that if you say that, and so we're preparing ourselves for like the last class or two of the semester, if we believe that light is a wave, that means we believe that there is a medium of things that are wiggling back and forth, oscillating harmonically back and forth in order to create this phenomenon called light. And if we believe that, we have a responsibility to figure out what the heck that medium is. That's like the last big question, the last big issue to tie up before the whole semester, but it's like the most important issue of all time, like in physics. I'll say it one last time and then we'll go. I'm saying, if we believe sound is a wave, that means we don't believe that there's any such thing as sound. We believe we have a bunch of things called air molecules that oscillate in an intricate pattern to send sound through. If we believe that light is a wave, that means we're saying light is not a thing. There are no such things as bits of light, but that there is some bunch of things somehow vibrating and oscillating, some kind of medium to send the light through. Our last question of the whole semester is, if light is a wave, what the heck is its medium? Raise your hand if you understand the question. Oh, I see something in the chat. I'll get back to that chat next week, but that's pretty cool. I don't know what it means, but I do. But raise your hand if you understand the question. Yes. Okay, cool. If you understand the question, then awesome. Okay, cool. Or raise a thumb up, cool. And goldfish, yes. Okay, so great. You guys have been awesome. If you have any catching up to do for me, please do it. But mostly I have catching up to do for you. I will see you next week. And I think last week, and then I do, wait, last week. Next week is the last time I see you, correct? Is that, wait, yes. Okay. All right, so cool. So have a great week. Have a great week. Bye.
I have a question about the game. I submitted up to the 11th. There is no more.
Did I not put one today? I thought I did. Wait, I might have accidentally, I may have